in statistics, especially in testing of hypothesis or maybe in general inference problem, sometimes we encounter with a problem of developing or deriving the distribution of a particular statistic, or sometimes in case of testing a particular test statistic, at least when at least under H naught. But in many situations we have seen that the derivation of the distribution of the test statistic or the statistic itself maybe under H naught or under alternative might be very, very complicated, and sometimes it is difficult to get the distribution in a very compact form through which we can actually do the testing, or we can find the alpha percentile cutoff point. But if the sample size is large, the question is, this is true for fixed sample, this usually happens for fixed sample size. Now the question is, can we gain something or can we make our life little more comfortable if we have a large sample size? Because now everyone is asking for what is the sample size should be large, like that. We have already learnt one important theorem or result, that is Taylor expansion in probability, both in univariate as well as multivariate case. Now today we are going to discuss its application of this Taylor expansion in large sample theory of statistical inference in order to develop or derive the distribution, or which might help us in deriving the distribution of the test statistic, which is otherwise very, very complicated. And in this context, I am just mentioning the name, one important theorem that we often hear, that is called delta method. So today we are going to discuss that delta method and along with its proof, and we will see with example that how this delta method can be applied. Actually delta method is nothing but a consequence of Taylor's expansion in probability. This can be applied in deriving the distribution of a complicated statistic or complicated function of some sample statistic. The basic objective of today's talk is that we are trying to find out a general theorem of finding in order to find the asymptotic distribution of a, say, test statistic which is otherwise very difficult to get, but this is only for large sample size. And the most important and very commonly used method is known as delta method. We are going to state and prove this delta method and also extend this in case of multivariate or rather random vectors or sequence of random vectors or functions of random vectors. So first we state the Taylor's expansion in probability. Let xn be a sequence of random variables such that xn equals to a plus big O p of Rn, and Rn is a sequence of positive real numbers which goes to 0 as n goes to infinity. Now if g is a function having derivatives of up to order s at a, then we have, by Taylor expansion in probability, we can immediately write that g of xn equals to summation j equals to 0 to s jth derivative of g at a xn minus a whole to the power j divided by j factorial plus small o p of Rn to the power s, where g0 equals to g. And natural extension of this Taylor expansion in probability is in case of multivariate distribution or multivariate vectors, random vectors, we can state like let xn be a sequence of random k vectors such that xn minus a, both are vectors or sequence of vectors, equals to big O p of Rn, and Rn is a sequence of positive real numbers that goes to 0 as n approaches to infinity. Now if we consider a function g which is a function from Rk to R such that the derivatives, partial derivatives del del xi of g are continuous in a neighborhood of a, then this multivariate version of Taylor expansion in probability states that g of xn equals to summation j equals to 0 to k del del xi of ga into xni minus ai plus small o p of Rn. Now we are going to give a definition which we will use very, very frequently later on. A sequence of random variables xn, remember for the moment we are again considering the sequence of random variables xn is said to be asymptotically normal with mean within quote mean mu n and within quote standard deviation sigma n if sigma n greater than 0 for all sufficiently large n, and xn minus mu n by sigma n converges in distribution to z where z follows normal 0 1. That means z follows a standard normal distribution. Using Surfling actually used this notation, and following Surfling's notation we are introducing the same notation here. Xn follows an stands for asymptotically normal with mean mu n and sigma n standard deviation sigma n, and we will explain, we will mention that this mu n is not the mean of the asymptotic distribution. So this is just a jargon, and the meaning of that xn follows asymptotically normal with mean mu n and sigma n means xn minus mu n by sigma n goes to or approaches to a standard normal variable as n goes to infinity in distribution. So naturally this does not necessarily mean that expectation of xn equals to mu n or variance of xn equals to sigma n squared. Now this famous theorem is stated as if xn follows asymptotically normal with mu n and sigma n, where sigma n goes to 0 as n goes to infinity, and if g is a function which is differentiable at mu, then g xn follows asymptotically normal with mean g mu and variance g prime mu whole square into sigma n square. So the interesting thing is that the mean function is very simple, just replace xn by the corresponding expectations, but or mu the parameters, but the variance function is also not very complicated except that it involves only the first derivative of g function at mu. Since first define Zn equals to xn minus mu by sigma n, and it is clear that this goes to a standard normal variable z in distribution as n goes to infinity, we can immediately write that capital Zn equals to big O p of 1 as n goes to infinity, which immediately implies that capital Xn equals to mu plus big O p of sigma n, using the previous results based on orders in probability. So by the previous result we can immediately write that sigma n to the power minus 1 gxn minus gu equals to sigma n to the power minus 1 g prime mu into xn minus mu plus small o p of 1. Again, from the asymptotic distribution of Zn equals to sigma n to the power minus 1 into xn minus mu, it is clear that g of xn follows asymptotic normal with mean g mu and variance g prime mu whole square sigma n square, which follows immediately from the previous line. So this method is known as the delta method. So basically this delta method, proof of delta method is a direct consequence of few results in orders in probability and a Taylor's expansion But this delta method has immense importance in statistics, especially in the large sample theory. So we are not going to define we are now going to prove the same kind of delta method for a sequence of random vectors or involving sequence of random vectors. So let us first define that a sequence of random vectors of dimension k xn is asymptotically normal with mean vector mu n and covariance matrix capital sigma n if sigma n has no zero diagonal elements for sufficiently large n, and lambda prime xn follows asymptotic normal with mean lambda prime mu n and variance lambda prime sigma n lambda for every lambda belonging to Rk, such that lambda prime sigma n lambda greater than 0 for sufficiently large n. So again, just if we look at the condition 2, it immediately says that we are again trying to look at this random vector or the sequence of random vectors in terms of a linear combination of the components of this random vector. That means we are trying to make this univariate from the multivariate. Now, we shall describe one theorem which is nothing but the multivariate analog of the previous theorem, that means the delta method. Suppose xn, the sequence of random vectors, follows asymptotic normal with mu vector mu, mean vector mu, and dispersion matrix Cn square sigma, capital sigma, where capital sigma is a symmetric non-negative definite matrix and Cn goes to 0 as n goes to infinity. Suppose that gx equals to g1x, g2x up to gmx prime. So, that means gx itself is a vector, that means it is a mapping from Rk to Rm into Rm such that each gi is continuously differentiable in a neighborhood of mu, and capital D, capital sigma, capital D prime, that means d sigma d prime has all non-zero diagonal elements, where we defined D as a matrix involving the partial derivatives of ith component of g function with respect to jth component of x. So, this is matrix of del del xj of gi mu, where I equals to 1 to n, j equals to 1 to k. Then it can be shown that g of xn follows asymptotic normal with g mu and dispersion matrix Cn square d sigma d prime. So, proof of this will follow again, following almost the same line that we have already proved in case of delta method for univariate setup. So, the sequence of random vectors xn follows asymptotic normal with mean vector mu and dispersion matrix Cn square sigma, which immediately implies that x in j, that is jth component of x vector, follows asymptotic normal with mean mu j and dispersion matrix Cn square sigma jj, where sigma jj obviously strictly positive is the jth diagonal element of capital sigma. Clearly, Cn to the power minus 1 x nj minus mu j converges in distribution, and hence it is always bounded in probability. So, immediately we can write x nj equals to mu j plus big O p of Cn. Now, use multivariate Taylor expansion in probability. For I equals to 1 to m, we can write gi of xn equals to gi mu plus summation j equals to 1 to k del del xj of gi mu into xnj minus mu j plus small o p of Cn. That means, we are actually applying this Taylor expansion, multivariate Taylor expansion in probability to the each component of the g function, and in this case we have m component g function. Now, in terms of vector using vector notation, we can write this first line as g of xn minus g of mu equals to d into xn minus mu plus small o p of Cn, or just Cn inverse into g of xn minus g mu equals to Cn inverse capital D into xn minus mu plus small o p of 1. Since Cn to the power minus 1 d xn minus mu follows asymptotic normal with mean vector 0 and dispersion matrix d sigma d prime, then using Statsky's theorem and the previous using the previous approach, we immediately have Cn to the power minus 1 into gxn minus g mu follows asymptotic normal with mean 0 0 vector and dispersion matrix d sigma d prime. So, that actually concludes the proof in case of multivariate distribution for the delta method. Now, we will give one interesting example, which is very this example is also very useful and important in statistics, especially in large sample theory, that we will derive the asymptotic distribution of sample coefficient of variation. Now, we know that it is difficult to derive the distribution of coefficient of variation, although using the fact that if we have a large sample size, that means when n goes to infinity, we are able to derive the asymptotic distribution of the same statistic, that is sample coefficient of variation, and the form is really compact and nice. We will see how it can be done. So, let xn be an IID sequence, that means independently and identically distributed sequence of random variables with expectation of xn equals to mu, variance of xn equals to sigma n square, expectation of xn square equals to mu 2, which is nothing but mu square plus sigma square. We also define expectation of xn to the power 3 equals to mu 3, and expectation of xn to the power 4 as mu 4, which we assume to be less than infinity, that means finite quantity. So, all moments below order 4 up to order 4 exists. Then sample coefficient of variation is defined as a mu n, which is Vn, which is equals to Sn by xn bar, where xn bar is nothing but sample mean and Sn square is nothing but the sample variance. From Clt of sample moments, we know that xn bar and 1 by n summation xi square follows asymptotic normal with mean vector mu comma mu 2 prime, or mu and mu 2, and dispersion matrix sigma by n, where this capital sigma is nothing but the matrix whose ijth component is given by mu I plus j minus mu I into mu j, with mu 1 equals to mu. Now, we can write Vn as a function or two variable function of xn bar and 1 by n xi square, which we call g, where g xy equals to x to the power minus 1 into y minus x square whole to the power half. So, direct application of theorem 2, we have Vn follows asymptotic normal with mean sigma by mu and dispersion matrix as capital D sigma capital D prime by n. Now, it is important to note two things. The first thing is that this mean, or asymptotic mean I should say, sigma by mu is nothing but the population coefficient of variation, Vn is the sample coefficient of variation. So, when the sample size is large, we can assume that, or we can have a feeling that the sample coefficient of variation will probably be very close to this population coefficient of variation, or the distribution of sample coefficient of variation should be around population coefficient of variation, which is in fact true. And this dispersion matrix is obtained by assuming by calculating capital D, where capital D is nothing but del del x of g mu and del del y of g mu, which is in fact minus mu 2 by sigma mu square and 1 by 2 sigma mu. So, just a little manipulation will give us these values. So, this delta method gives a very easy and elegant way to derive the asymptotic distribution of sample coefficient of variation. Now, remember, this is just an example. One can construct any test statistic, maybe involving 2 or 3 statistics or more than one statistics at the same time through a function, and one can always get the asymptotic distribution using delta method, provided some very weak conditions are satisfied, like continuity and derivability up to a certain order. So, although at the first look this delta method or this expansion which eventually led to the delta method looks sometimes slightly complicated, but if you look carefully, this is not really complicated. In fact, it is very easy. It involves only the first order differentiation of the function, for which we are going to derive the asymptotic distribution. And delta method is extremely easy to apply, as we have already seen. And if we look at if we consider the example that we have discussed, that is the how to find the asymptotic distribution of sample coefficient of variation. Now, sample coefficient of variation, if we look at this function, is the ratio of standard deviation by mean, sample mean, and this ratio is not a very easy function. But application of this delta method, immediate application of delta method leads us to a fine or nice form of the asymptotic distribution, and in fact the asymptotic distribution is nothing but normal. So, this gives us a confidence that we can apply delta method in many situations when we are actually not capable of deriving the exact distribution of the statistic.